Welcome everyone, I'm Norman Wahlberger. In our last few videos we introduced the multiplication table. First the 5 by 5 and then the 10 by 10 multiplication table, which takes students somewhere around grade 3 almost a year to develop, learn, master. So it's quite a significant accomplishment, and today we want to talk about a few tricks, small little insights that can help students to learn this table and to become familiar with it. Okay, so the first trick, which is not really a trick, it's just a basic useful fact, is that when we want to multiply by 10, we just add 0 to a number. We add 0 to the right hand side. So for example, 10 times 3 is 30. What we get when we take the 3 and we just add a 0 on the right. And that's the same as 3 times 10. 3 times 10 is also 30. We're multiplying by 10, so the 3 gets changed by having a 0 attached to the right. Now you can check in the 10 by 10 multiplication table that that's always the case, but in fact it's a more general fact, as we'll see a little bit later, that whenever we multiply any number by 10, the same thing always happens. We just end up attaching an extra 0 to the right hand side. So the ones get shifted to the tens get shifted to the hundreds, and so on. That's another way of thinking about what's happening. Okay, so when we present a fact like this, we should also pay a little bit of attention to the natural question, well, why is it true? So you shouldn't just accept these statements because I'm telling you. Yes, you should generally believe what I'm telling you, but there should also be a sense of evidence presented, of a reason given that explains, or at least somewhat indicates, why a particular fact is true. So let's have a look here and see why this is true, if we can see the general pattern that makes it clear. So when we say 10 by 3, I remind you that we're talking about a rectangle that has this shape. 10 by 3. Another way of thinking of it is we're adding up all these rows. There are 10 rows and each one of them has 3. So it's like 3 plus 3 plus 3 plus 3 all the way down 10 times. That's what 10 times 3 means. While 3 times 10 is the number of little squares in a rectangle of size 3 by 10. 3 this way, 10 this way. And what that means for us is it's 10 plus 10 plus 10. Now we've seen the basic fact of commutativity of addition. The number of cells in this rectangle is the same as the number of cells in this rectangle, because to go from this rectangle to this one, we just take this one and flip it on its side. It doesn't change the number of little cells in it. That's our basic reason why the commutative law in multiplication holds. So this interpretation is of 10 groups of 3. 3 plus 3 plus 3 plus 3 and so on 10 times. While this one here, the interpretation is 3 groups of 10. So it's 10 plus 10 plus 10. Alright, so now let's ask ourselves, why is it that when we multiply by 10, we get 30? We get the 3 with a 0 attached. Well, let's have a look at 30 in the Hindu-Arabic system. What does that actually mean? That number represents 3 tens and 0 ones. That's what it means. 0 ones, 3 tens. Remember, that's the ones place and that's the tens place. 3 tens and 0 ones. So where can we see 3 tens and 0 ones? Right here. This picture right here is exhibiting 3 tens. 10, 10, and 10. So when we look at it this way, in terms of 3 times 10, we're seeing 3 groups of 10, and that's why we're getting the 3 groups of 10, the 3 in the tens place. because 3 times 10 means 3 groups of 10. And there are no zeros because there's just 3 groups of 10 and that's all. That's why we're getting 3, 0, or 30 when we multiply 3 by 10. That's a bit of an explanation, and I hope you can see that if we change the 3 to a 4, say, then the only thing that would be different here is that there would be then 4 rows here, so we would have 4 groups of 10. So 4 times 10 would be 40, because 4 groups of 10 would be 4 10s and 0 1s. So this is a very important fact to appreciate, that multiplying by 10 in our system is particularly easy. I've sometimes seen with consternation young people, maybe at the checkout counter, having to reach for their calculator when they have to multiply by 10 or by 100. Okay? Multiplying by 10 is very simple, and primary school students ought to know that it's just a case of adding a 0 to the right. For our next little trick or observation, let's go back to the multiplication table. This is the same slide as on our previous video, and just have a look at it again. There's a 10 by 10 multiplication table, so 7 times 8 is 56, 9 times 3 is 27, 10 times 6 is 60, and so on. Okay, there's some nice patterns here, and the next observation has to do with the even-odd dichotomy for numbers. Let's have a look at the multiples of 2. These are the even numbers. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. The even numbers always end in either a 2, a 4, a 6, an 8, or a 0. The odd numbers are the other ones. The 3, or the 1, I suppose, and then the 3, and then the 5, and the 7, and the 9. And all numbers that end in 1, 3, 5, 7, or 9 are the odd numbers. Alright, so if we look at the table, we notice something, that if we multiply by 4, we always get an even number. If we multiply by 6, we always get an even number. If we multiply by 8, we always get an even number. When we multiply by 10, we always get an even number. So whenever we multiply by an even number, the result is an even number. What happens if we multiply by an odd number, say like 3? Well, in that case, the result is odd or even. Odd or even. Odd or even. Odd or even. It depends on what we're multiplying the odd number by. If we're multiplying the odd number by another odd number, like 1, we get another odd number. 3 times 3, that's another case of odd times odd. That's also odd. 3 times 5, that's odd. But as we've seen before, if we multiply 3 by an even number, then we get an even number. That's a very simple kind of rule, but it's important enough to be isolated and identified. Maybe it's almost like a trick. So let's record this, call it trick number 2, which we might say is pay attention to even and odd. Just to remind you, they are the even numbers. Of course, they keep on going. They're the odd numbers. Of course, they keep on going too. And as we count, the numbers alternate odd, even, and so on. And the rule that we've identified is that if we multiply an even number by an even number, well, we get an even number. If we multiply an even number by an odd number, we still get an even number. An odd number times an even number is also even. The only way we can get an odd number is when we're multiplying an odd number by an odd number. In that case, we do get an odd number. So one way this is useful is that it's sometimes a check on multiplication. When we're dealing with numbers, at the back of your mind, you should be aware of whether a number is odd or even. Sort of like black or red at the roulette table. Okay, there's this basic division in numbers between even and odd. And if we remember these rules, then sometimes it can alert us to when we've made a mistake. For example, if someone claims that 7 times 8 is 59, or perhaps you are trying to remember what 7 times 8 is and you can't quite remember, and you know, well, it was 50 something. What was it? Could it be 59? Well, the answer is it couldn't be 59 because here we have odd times even, and odd times even has to be even. So there's no way that that could be 59. It couldn't be 57 either. It couldn't be 55. It has to be an even number. In fact, 7 times 8 is 56, which of course is an even number. So this is a very useful rule to remember to check your multiplications. So after multiplying by 1, multiplying by 10, multiplying by 2, the next simplest multiplication is multiplying by 5. And there's a trick that applies there, or an observation, and it is that multiples of 5 always end in either 0 or 5. And 5 times an even number has to end in 0, while 5 times an odd number ends in 5. So the way the multiples of 5 work, let's go through the multiples of 5. So 1 times 5 is 5. 2 times 5 is 10. 3 times 5 is 15. 4 times 5 is 20. 5 times 5 is 25. 6 times 5 is 30. 7 times 5 is 35. 8 times 5 is 40. 9 times 5 is 45. And 10 times 5 is 50. So you can see they're alternating, ending in 5 or ending in 0, depending whether we're multiplying by an odd number or an even number. And an explanation for, say, why 5 times even ends in 0 could be given this way. So if you have 5 times an even number, well, an even number is actually a multiple of 2. So it's 2 times something. The something we don't know, let's call the something n, just for something to represent that unknown thing that the even number is. So we're talking about an even number which is 2 times n. So we multiply by 5, we're getting 5 times 2 times n. But the associative law for multiplication, which is one of our very important laws that we're going to be talking about, tells us that we can rearrange this kind of multiplication so that it's now 5 times 2 times n. So we can combine the 5 and the 2 first, multiply them together, and then multiply by n. Alright, so if you believe that, if you accept that for a moment, then the 5 times 2 becomes the 10, and then we're talking about 10 times n, and we know that when we multiply by 10, we get a 0 at the end. That's the reason why when we multiply 5 by an even number, we're getting a 0 at the end, because it's really 10 times something else. That's some kind of explanation for this one here. So we're using this associative property of multiplication, which is, we'll see that's a very important law or pattern or rule that multiplication satisfies. And here's just another example of it, that 5 times 2 times 3. When you have 3 numbers multiplying together, you have a sort of a choice as to what 2 numbers you're going to multiply together first. If we multiply the 2 and the 3 together first, 2 times 3 is 6. So this will become 5 times 6, which according to our table is 30. On the other hand, if we group this a different way, if we group the 5 and the 2 together and agree to multiply those 2 together first, then 5 times 2 times 3 is 10 times 3. And then again, using the table, 10 times 3 is 30. And so, we see that, at least in this case, whether we multiply things in this order or in this order, the result happens to be the same. That's called the associative law of multiplication. Alright, so our next trick has to do with multiples of 3. And the multiples of 3 have a very pleasant property. Not quite as simple as even or odd, but it's still quite pleasant. And here's what it is. It's a little bit tricky. Any multiple of 3 has digits which add up to a multiple of 3. Let's see what that means. Here are the multiples of 3, or at least the first 10 or so of them. The multiples of 3 are 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, 3 times 6 is 18, 3 times 7 is 21, 3 times 8 is 24, 3 times 9 is 27, and 3 times 10 is 30. Let's have a look at these multiples of 3. What we're saying about them here is that if you add up the digits, you get another multiple of 3. So here, here, and here, there's only one digit. If we add up the digits, we're just talking about the single digit. And yes, 3, 6, and 9 are multiples of 3. What about 12? So the digits there are 1 and 2. If we add up 1 and 2, 1 plus 2 is 3. And 3 is another multiple of 3. 1 plus 5 is 6. Yes, that's another multiple of 3. 1 plus 8 is 9, which is a multiple of 3. 2 plus 1 is 3 again. 2 plus 4 is 6. 2 plus 7 is 9. 3 plus 0 is 3. In fact, if you kept on going, you can try. Keep on adding 3, and then adding up the digits, you will get another multiple of 3. So again, this is another little trick to help us when we're multiplying by 3 to recognize, or maybe to check, that we've done things right. If we say are asked what's 3 times 6, and maybe we think it's 20. Well, 3 times 6 can't be 20 because the sum of the digits in 20 is 2. And 2 is not a multiple of 3. So there's no way 3 times 6 could be 20 if we had forgotten what it actually was. The number 9 has a kind of special place in our number system because it happens to be the last of our digits, the biggest digit by itself. After 9, you have to use 2 digits to express a number. And that means that 9 plays some interesting role. And our fifth trick is telling us that the multiples of 9 have very similar property to the multiples of 3. Namely, any multiple of 9 has digits which add up to a multiple of 9. So it's exactly the same rule as for multiples of 3, having digits which add up to a multiple of 3. So let's have a look at the multiples of 9. They form a very nice pattern. A pattern that's easily remembered, I think. Let's have a look. So 9 times 1 is 9. 9 times 2 is 18. 9 times 3 is 27. 9 times 4 is 36. 9 times 5 is 45. 9 times 6 is 54. 9 times 7 is 63. 9 times 8 is 72. 9 times 9 is 81. And 9 times 10 is, of course, 90. And if you look at these numbers, I hope you see some patterns. First of all, the digits add up to, well, they all add up to 9. 1 plus 8 adds up to 9. 2 plus 7 is 9. 3 plus 6 is 9. 4 plus 5 is 9. 5 plus 4, 6 plus 3, 7 plus 2, 8 plus 1, 9 plus 0. They all add up to 9. So any multiple of 9 has digits which add up to a multiple of 9. That's certainly true for the first 10 multiples of 9, where the sum of the digits is in fact just 9. But we state the rule this way because, in fact, the rule applies even if you go beyond 90 to higher multiples of 9, like 99. The next one will be 108, and so on. The same rule still applies. Now, because each of these add up to 9, we see that as the tens digit increases by 1, the ones digit decreases by 1 each time. So that the total is always 9. So we're going from 1,8 to 2,7. The ones has been jacked up to 2, while the 8 has gone down to 7. Then for the next step, 2 goes to 3, 7 goes to 6. The tens is incrementing by 1, the ones is decreasing by 1. So at each step, the tens digit goes up by 1, while the ones digit goes down by 1. And another way of seeing why that's true is when we add 9 to a number, it's really the same thing as adding 10 and then subtracting 1. So that's useful to remember that 9 is 10 minus 1. The reason why it's useful to relate it to 10 is because 10 is very fundamental in our number system. Things work very well and simply with tens and powers of 10. So if we can relate something to 10, chances are it'll be easier to remember. And that's why multiplication by 9 is one of the easier ones on the table to remember, even though it's in fact almost the last row. So a related trick is this one. To multiply a number by 9, what we can do is we can multiply by 10 and subtract the number. So we perform 2 steps instead of 1, but the advantage is that each of the steps is relatively easy. So for example, 9 times 6, and I remind you that that's 9 copies of 6. 6 plus 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 6. 9 sixes. What we're saying is that's the same thing as 10 times 6 minus 6. So we might as well take 10 copies of 6 and then subtract a 6. And the reason why that's easy is because multiplying by 10 we've seen is very simple. You just add a 0 to the right. So 10 times 6 is 60, telling us that 9 times 6 is 60 minus 6. To take away 6, take away 6 from 60, you get 54. So if you've forgotten what 9 times, say, 6 is, you can figure it out this way. It's one way of remembering or recalling how to multiply by 9. So these are all useful little tricks to help us multiply, also to give us more familiarity with the pattern of numbers and how they interrelate. It's a very important experience that young people, or not so young people, who want to learn mathematics well need to have. A familiarity with the numbers from 1 to 100 roughly. Various patterns that they form. Mathematical patterns. When young people are learning the multiplication table, they need lots of practice. It's not just a question of telling them things. It's important for them to do things, to do lots of exercises and problems, to use pen and paper, or better, pencil and paper at that age, to write down solutions to lots of problems. That's the best way of solidifying the knowledge, is to put it into practice in an active form. And I encourage the pencil and paper approach rather than the keyboard computer approach. Okay, I think it's fundamentally better to actually write down the numbers 4, 5, 6, rather than just press a particular key. All right, so let's have a look at just a very select few kinds of problems. 3 times 6. What is 3 times 6? Well, hopefully the student will know at some point. But when they're starting out, they don't just know. They have to scratch their head and try to remember, and maybe they can remember and maybe they can't. And if they can't, I hope they can figure it out. And how could they figure this out? Well, they could do it in a number of ways. One way would be to write down or draw a rectangle of sides 3 and 6. Let's do it right here. Okay, so I'm going to draw a rectangle that has 3 rows and 6 columns. So there's 1 column, 2 columns, 3 columns, 4 columns, 5 columns, and 6 columns. Okay, there's a fair amount of work. So that's now a 3 by 6 rectangle that we've created. And now we can count how many entries there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that would be one way of calculating what 3 times 6 is. Another way would be to say, well, 3 times 6 is 3 groups of 6. We're talking about 6 plus 6 plus 6. So what is 6 plus 6? Well, hopefully the student knows that that's 12. So that's 12, and then we still have to add 6 more. And the student can do that in a number of ways. Maybe they just take 12 and then go 13, 14, 15, 16, 17, 18. We're adding 6 more to 12 to get 18. Another way might be that they know what 3 times 5 is. They know that 3 groups of 5 is 15. Well, 3 groups of 5 is 15, then 3 groups of 6 will be 3 more. So 15 plus 3, also 18. But hopefully once they've made this calculation, they figured out that 3 times 6 is 18. Maybe someone has come along and checked it. Hopefully at that point they might pause and say, all right, I need to remember this now. I didn't know it before. I figured it out. It is correct. Let's see if I can commit this to memory. 3 times 6 is 18. 3 times 6 is 18. 3 times 6 is 18. I'm going to repeat this to myself 10 times. And then hopefully next time I see 3 times 6, I will know that it's 18. I will remember that it's 18. I won't have to go through figuring it out one way or the other. But in case I do forget, I'm still confident that I can figure it out either by drawing a rectangle or by converting it to a bunch of additions. All right, so I'll leave the other ones in this problem for you to work out. In this second question, we're asked to find the mystery number. So it's another aspect of knowing the multiplication table. It's a little bit more subtle now. So now we want to know what mystery number, represented by that question mark, do we need so that 4 times the mystery number is 24. So you need to know the multiplication table perhaps in a slightly different way. You need to know that 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12, 4 times 4 is 16, 4 times 5 is 20, 4 times 6 is 24. 4 times 6 is 24. Okay, so 4 times 6 is 24. That means that our mystery number, question mark, is actually 6. And I'll leave these ones here for you to figure out. In this third question, we're asked to insert the correct relation. The less than relation, the equals relation, or the greater than relation. Let's have a look at the first one. We have 2 numbers, 3 times 5 and 2 times 7. We want to know what's the relation. Which one is bigger? Which one is smaller? Or perhaps they're equal. So we have to calculate what is 3 times 5. Well, that's a 5 by 5 table one, so hopefully we've already learned that. 3 times 5 is 15. We know that. 2 times 7, that's one of the new ones that we've learned by going up to the 10 by 10 table. And 2 times 7, hopefully we figured out that that's 14. Another way of thinking about it, it's 7 plus 7. No, 7 plus 7 is 14. So now we are asked to compare 15 with 14. Well, they're not equal. Which one of them is bigger? The 15 is bigger. So the 15 is bigger than the 14. That means we choose this sign. This is the greater than sign. 15 is greater than 14. And you can remember which side the bigger thing is on, because the thing is sort of opening up towards the bigger number. So we read 15 is greater than 14. And I'll leave the other ones for you to do. So now here are some word problems involving multiplication. Problems where we need to do some multiplication, but we also need to read the question, interpret the question, and then ultimately give back an answer in written sentence form, or pretty close to sentence form. The closer, the better. So let's have a look at the first question. What is the area of this rectangle? Okay, so we can see it's a rectangle there. I suppose we could start counting. 1, 2, 3, 4, 5. We could do that, but we're not going to do that because we recognize that areas of rectangles is essentially multiplication. That's the fundamental interpretation of what multiplication means. So let's do it using multiplication. To do that, we need to find out how many rows it has. 1, 2, 3, 4. There's 4 rows. We'll put a 4 there. And how many columns? 1, 2, 3, 4, 5, 6, 7, 8, 9 columns. I'll put the 9 there. So now I can write down the expression for the area. It's 4 times 9. That's what 4 times 9 means. It means the number of little cells in a 4 by 9 rectangle. And I can compute 4 times 9 in a number of ways. Maybe I've just memorized it from the table. Or I could compute it by saying, well, this is 9 plus 9 plus 9 plus 9. Then I have to do a bunch of additions. 9 plus 9 is 18. Plus 9 is 27. Plus 9 is 36. That would be one way. Another way would be to say, well, 4 times 9, that's like 4 times 10 minus 4. Remember, multiplying by 9 is like multiplying by 10 and then subtracting one of the things that we're multiplying. So another way of calculating this would be to say, well, it's the same as 4 times 10 minus 4. Or 40 minus 4, which would also give us 36. So either by memorizing the table, or by making an addition, or by using some trick, we calculate that 4 times 9 is 36. And so finally we want to output that as a sentence answer. So we say the area is 36. Okay, we've written a sentence that answers the question, has the same word, the key word area in it, and it's a complete sentence with a bit of mathematics in there too. All right, our second question. Tom gets 3 meals a day for a week free in a resort. How many free meals altogether does he get? So he gets 3 meals for the first day, 3 meals for the second day, and so on for a week. How much is a week? Well, 1 week, we need to know, equals 7 days. So we're getting 3 meals a day for 7 days. So it's 3 plus 3 plus 3 plus 3 plus 3, 7 times. So the answer is 7 times 3. 7 groups of 3. And 7 times 3, well, we can calculate that in a number of ways. Hopefully we already know it from the multiplication table, but if not, we could work it out by, say, knowing that 5 times 3 is 15. And so if we add another 3, that would be 6 times 3, that would be 18. And then to get 7 times 3, we'd add another 3 on top to give us 21. So that's the calculation that we make. And then we write down a solution. So he gets altogether 21 free meals. So we've answered the question in an English sentence with the answer that we've computed over here in it prominently. So for our third word problem, we're asked how many legs in a herd of 8 horses. A herd of 8 horses. Well, let's write it this way. Each horse has 4 legs. That's an important fact. We're talking about horses, not people. If it were 8 people, it would be different from 8 horses. But 8 horses, each horse has 4 legs. So we write that down. Each horse has 4 legs. So altogether, so in total, there are, and I'm going to write down the multiplication that we need to do. We've got 8 horses, each one of them has 4 legs. So it's 4 plus 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 4. I hope that was 8 altogether. So we're doing 8 groups of 4. We need to know what 8 times 4 is. So from our multiplication table, 8 times 4 is 32. So we're going to write, so in total there are 8 times 4 equals 32 legs. And it's all right to include that equation like that. That's in some sense explaining where the 32 comes from. That you're making this calculation, 8 times 4, there are 8 horses, each horse has 4 legs, and that's the total that we're getting from the multiplication table. So for our last question, each guest at Sue's party had 6 salmon crackers. Altogether, 48 crackers were eaten. How many guests were at the party? This is also a multiplication table question, but it's a little bit more subtle. Because we don't know how many guests there were. It's a mystery to us. But each one of them eats 6 crackers. So I'm going to represent the mystery number by a question mark, which is not very sophisticated, but I think it expresses the idea quite well at this stage. So this is the number of guests. What do we know? We know each guest eats 6 crackers. So the total number of crackers eaten is the number of guests times 6. Each guest eats 6 crackers. 6 crackers plus 6 crackers plus 6 crackers plus 6 crackers. Altogether as many of such groups as there are guests. And we're told that altogether that comes to 48 crackers. So we need to find the mystery number. What times 6 equals 48? So you have to look down the multiplication table, essentially down the column that has a 6 on it, and see where in that column you're going to get a 48, and then look across to what row you're in. So another way of doing it is to think of multiples of 6. 5 times 6 is 30. 6 times 6 is 36. That's a square. 7 times 6 will be 42. 8 times 6 is 48. Ah, that's exactly what we want. 8 times 6 is 48. So we can maybe write mystery number equals 8. This sort of expresses our thinking. We have some mystery number times 6 equals 48. And by going through the table, we figure out that the mystery number has to be 8. And then we express that in a final sentence. We're asked how many guests were at the party. So we write, there were 8 guests. And we've solved the problem. All right, so very good. We're getting some more experience with multiplication, this very, very important task of learning the multiplication table and applying it to problems that involve multiplication and recognizing when a problem involves multiplication. Next time we're going to look at some geometrical applications of multiplication, going back to the basic orientation of a multiplication representing an area of a rectangle. But we're going to look at some more sophisticated problems that involve a little bit of lateral thinking too, and that introduce a little bit of a challenge for young people. A way of practicing multiplication and also being maybe challenged at the same time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.